All right, well, today I want to talk about the n-body problem. Let me get a share screen going. This is actually a homework problem in COS 415, modeling and simulation. And in 415, we talk about the inverse square law. That's a central force. Newton gave us that the magnitude of the force between two masses is gm1 m2 over the distance between them squared, and this is the magnitude. He also gave us the fact that it was a central force. The force vector is along the vector between the two masses. If we look at this in radial coordinates, we have the RdT term, and we have the d theta dt term being 0. This is this implies conservation of angular momentum. So how am I going to solve this? Well, looking at this from the point of view of vectors, we have a vector force. This is a force in a direction. This has magnitude gm1 m2 over r squared, and it's in the direction of this r vector between them. So this term right here is a unit vector, r divided by its magnitude, in the a unit vector in the r direction. So I can bring these two together into this r cubed, and my force is minus gm1 m2 over r cubed times the vector between them. This r cubed often throws people off. So we're looking at second order differential equations. And if I resolve r into its x and y components, and of course in Unity I'll do it in x, y, and z, I have two coupled equations, one in x and the other in y. And these are coupled through the fact that r is the square root of x squared plus y squared, the magnitude of the vector between them. And of course, in 3 dimensions, there'd be a z squared term and a z equation. We solve second order equations by decomposing them into two coupled first order equations. First, we have that the acceleration, which is f over m, is the rate of change of velocity. And the velocity is the rate of change of position, r. So we can write these two second order equations. Rate of change of velocity is gm2 over r cubed. Notice the m1 cancels out. And rate of change of position is velocity. Now, the reason we do this is because first order equations are easy to solve. From the definition of the derivative, the limit as delta t goes to 0 of r at t plus delta t minus r at t over delta t. If we drop that limit delta t goes to 0, and we replace r at t plus delta t by r at n plus 1 that's the n plus 1th step, and r of t is r at the nth step, then our approximation of the derivative is r at n plus 1 minus r at the n plus 1th step minus r at the previous step over delta t. And I can rearrange this so that I end up with a recursion relationship where I'm given r at the next step in terms of r and v at the current step and delta t. And analogously for the velocity, we have v at the n plus 1th step is v at the nth step plus that acceleration f over m times delta t. So we have our coupled first order equations. And remember, these are vector equations, so we actually have an x, y, and z component of each of these. So in Unity as code, this is really easy to implement. Our acceleration at the nth step is some function force over mass that we're going to solve given the position. We update the position with the velocity times the time step, and we update the velocity with the acceleration times the time step. And this is called the Euler method. A slight improvement called the Euler method updates the velocity and uses it immediately. So we get the velocity at the n+1 step, and we use it to project the position to the n+1 step. All we had to do was reverse the order of those two equations. There's also an Euler-Richardson method that kind of uses the midpoint. And there's Verlet's, which we'll probably use later on, and I won't go through any of how this stuff works. Oh, and there's also Runge-Kutta, which is kind of a little more complicated. Now, one approach to these is for each planet to have its own script that looks out into the world, finds all the entities tagged planet, calculates the force it feels due to them, and then moves itself. In our numerical method, Verlet is one that we're going to use back here, where we need velocity, acceleration, and then we do it again, do force over mass again at that new point, and average it with the original one. That's Verlet's method. And I'm going to stop right here and come back in and start this again with the actual code. So I'll stop sharing, and I'm going to end recording, and I'll pick this up in the next lecture. Bye.